All right, so now we're going to take a look at the inverse cosine function, and we're going to construct this in a very similar way to how we constructed the inverse sine function. So we're going to start with the graph of y equals cosine x. We run into the same problem we had with the sine graph, and that is this function is very much not one-to-one. The graph definitely does not pass the horizontal line test. So note we can't just do the same thing we did with sine x, where we restricted the domain from negative pi over 2 to positive pi over 2, because we run into two big problems. The first being that the graph we get is still not one-to-one, and we only get half the range because we miss the whole negative part of our graph. So instead, we're going to restrict our domain from x equals 0 to x equals pi. And then we're going to ignore the rest. And then that makes our function one-to-one when we restrict the domain. Our graph passes the horizontal line test, and we get the entire range of the cosine graph, everything from y equals -1 to y equals 1. Okay, so looking at this, we can construct the graph of the inverse cosine function. We can look at 3 points on the graph of this cosine. First, when x equals 0, y equals 1. So the point 0, 1 would translate to the point 1, 0 on the graph of the inverse cosine. Okay, next we have a point at pi over 2, 0 on our cosine graph. Okay, so that's going to translate to the point 0, pi over 2 on our inverse cosine graph. Okay, and then finally, on our cosine graph, we have a point at pi, -1. Okay, and that's going to translate to the point -1, pi on our inverse cosine graph. I just haven't leave myself quite enough vertical room here. So we'll have a point at -1, pi. Okay, so then we connect these 3 points, okay, and we get a graph that looks like this. And again, the shape of the graph is not terribly important to us, but what is important are the properties. Okay, so for the inverse cosine, we see the domain is -1 to 1. So the x values go from -1 to 1, which was the range of the cosine. Then the range of the inverse cosine is from y equals 0 to y equals pi, okay, which was the same as the restricted domain of our cosine graph. Okay, so what that means is when the inverse cosine reverses the regular cosine, it inputs a number between -1 and 1. Okay, so if we look at the inverse cosine of x, okay, and here just like with the inverse sine, I didn't explicitly state this, but x has to be between -1 and 1. For the inverse cosine to exist. So the inverse cosine of x is equal to theta, where two things have to be true. First off, theta has to be between 0 and pi, because that's the range of the inverse cosine. So we're spitting out an angle between 0 and pi whose cosine is x. Okay, so that is the definition of the inverse cosine. So it's a little different from the inverse sine because now the inverse cosine is not going to spit out an angle between negative pi over 2 and positive pi over 2. It's going to spit out an angle that's in either the first or second quadrant. Okay, so for example, the inverse cosine of 1 over square root of 2 is pi over 4. Okay, because pi over 4 is between 0 and pi, and the cosine of pi over 4 is 1 over square root of 2. Okay, or to do another example, the inverse cosine of 0 is pi over 2. Because pi over 2 rather, is between 0 and pi, and the cosine of pi over 2 is 0. Okay, or if we look at the inverse cosine of negative 1, that's going to be some angle theta, where theta is between 0 and pi. So theta is going to be in the first or second quadrant, or on the x-axis. And cosine of theta is negative 1. And the angle between 0 and pi, whose cosine is negative 1, is the angle pi. Okay, so for the inverse cosine, if you're doing the inverse cosine of a positive number, you're going to end up over here. If you do the inverse cosine of a negative number, you're going to end up over here. Now, one thing that I did not do with the inverse sine, but which applies to the inverse sine as well, is that if we try to find something like the inverse cosine of 2, this doesn't exist. Okay, because the inverse cosine of 2 would have to be some angle theta whose cosine is equal to 2. Cosines cannot equal 2. Cosines have to be between negative 1 and 1. Therefore, we cannot find the inverse cosine of 2. It does not exist. 2 is not in the domain of the inverse cosine. Okay. So finally, we'll look at the inverse tangent. So we'll start with the graph of the tangent function. Okay, so again, this function is not one-to-one, but we can make it one-to-one by just looking at the part between the asymptotes at x equals negative pi over 2 and x equals positive pi over 2. Okay, so now x equals plus and minus pi over 2 are not going to be included because the function does not exist there. So now we'll be looking at negative pi over 2 is less than x is less than positive pi over 2. And now if we turn this into the graph of the inverse tangent, okay, so a couple features we can look at. First off, we have on our graph vertical asymptotes at x equals negative pi over 2 and x equals negative, or positive pi over 2 rather. When we go to the inverse function, x and y flip, so now these are going to become horizontal asymptotes with equations y equals negative pi over 2 and y equals positive pi over 2. Okay, the point at the origin stays the same because you flip the coordinates of 0, 0, you still get 0, 0. We have a point here at negative pi over 4, negative 1, and we have a point at pi over 4, comma, positive 1. Okay, so they would flip to the points negative 1, comma, negative pi over 4, and positive 1, comma, positive pi over 4. Okay, so if we take all that information and collate it, we end up with a graph that looks like this. Okay, so that is the graph of the inverse tangent. Okay, so looking at our domain, the domain of the inverse tangent is all real numbers, same as the range of the tangent function. Okay, so now we can take the inverse tangent of any number because the tangent of an angle can be any number. So there's no restriction now on the x values we put in. If we look at the range is now going to be negative pi over 2 to pi over 2. Very similar to the range of the inverse sine, but without the endpoints. So now we can't have an output of negative pi over 2 or positive pi over 2 because the tangents of those angles are not defined. Okay, so now we have the fact that if, x is any real number, okay, so now we don't need the restriction that x is between negative 1 and 1. If x is any number, the inverse tangent of x is going to be some angle theta, where first off, theta is between negative pi over 2 and positive pi over 2, so either in the fourth quadrant, the first quadrant, or on the positive x-axis. And tangent of theta is x. Okay, so for example, if we wanted to find the inverse tangent of negative 1. Okay, that's going to be some angle theta that's in the fourth quadrant, the first quadrant, or the positive x-axis. So it's got to be somewhere in here. And the tangent of theta has to be negative 1. Okay, so that tells us that theta's got to be in the fourth quadrant with a reference angle of pi over 4. And so the angle we're looking for is negative pi over 4. Okay, that is the unique angle between negative pi over 2 and positive pi over 2, which has a tangent value of negative 1. Okay, or if we wanted to find the inverse tangent of 0, okay, that's going to be the angle theta between negative pi over 2 and positive pi over 2 with a tangent value of 0. And that angle is 0. Okay, because the tangent of 0 is 0, and 0 is between negative and positive pi over 2. Okay, so one final reminder when we work with inverse trig functions, when we had started to talk about graphs of trig functions and actually doing algebra of trig functions, I'd mentioned that we only work with radians, we don't work in degrees. Same is true for inverse trig functions. So the output of the inverse trig function is always going to be an angle, and that angle is always going to be in radians. Okay, so for the next set of videos, I will talk more about more advanced applications of the inverse trig functions, some ways that we can compose inverse trig functions with regular trig functions. So before you start to view some of those videos, make sure you're very solid on how to do these evaluations of inverse trig functions, how to find the inverse sine, cosine, and tangent of these numbers like we've talked about here today.